Here we've got a roller coaster, and we've noted six particular points on the roller coaster and then their relative heights from the ground. So the roller coaster is 1,000 kilograms, and this includes the mass of all the passengers, starts from rest, so V equals 0 at A, and then ends at F. We're going to look for the maximum speed, assuming the track is relatively frictionless. We're going to find the speed at point E, then we're going to find the braking distance required if the force of friction or the stopping force acting between E and F is 7,000 newtons. To get started, we should find the original amount of gravitational potential energy the roller coaster has, and that's going to be whatever EG is at its highest point. So that's obviously at point A. So the total amount of energy at point A is simply the kinetic energy plus the gravitational potential energy. But since we know that is starting from rest, we know that there's no EK. So this is going to go to 0. So the total amount of energy is simply going to be equal to the gravitational potential energy, which is m times g times h, which is the mass, 1,000 kilograms, times the acceleration due to gravity, 9.8 newtons per kilogram, times the height, 9.5 meters. This leaves us with a starting energy of 93,100 joules. From this point, we can then take a look at where the velocity is going to be greatest. So that is going to be where there's the largest change in h. So that's going to be at point D, because here we're going to have, we've gone from 9.5 meters at point A to 0.5 meters at point B. So that's going to give us the largest difference. So that's presumably going to give us the greatest value for velocity. What we know is that our total energy at point B is going to be the energy we kind of start with here, and equal to our kinetic energy plus our gravitational potential energy. So we know how much kinetic energy we have, given that we're coming from a with some amount of kinetic energy. So if I rearrange this equation, I end up with my kinetic energy is equal to my total energy minus the potential energy. This value for ET is going to be consistent throughout because conservation of mass says it has to be. EK is 1 over 2 mv squared equal to ET, which is 93,100, minus the gravitational potential at point D. So if you recall from the previous image, point D was 0.5 meters off the ground. So I can then start to substitute some values. So 1,000 for our mass, leave our total energy, then again 1,000 for the mass, times 9.8 newtons per kilogram, times our height. By rearranging and solving for v, we end up with a velocity of the square roots of 88,200 joules divided by 500 kilograms, which leaves us with a maximum velocity of 13.3 meters per second. The next part asks us to find the speed at E, so that's the same thing except now we have a definite point. In part A, we had to determine where we thought the maximum speed would be, so that's where your change in height is going to be the greatest. So for this part where we're solving for the speed at E, it's a little bit easier. So we have our total energy again equal to our kinetic energy plus our gravitational potential energy. And of course, we can rearrange this so that we have EK equals ET minus EG. And then we'll be able to go ahead and substitute some of our values in. So our mass again is 1,000 kilograms. We're solving for our velocity minus our gravitational potential energy. And our height at point E is only 5.5 meters. So I can rearrange this and solve. You end up with a velocity value of 9.8 meters per second. To solve for this last part, the braking distance, if the force of friction is 7,000 newtons. So we have some sort of force and we have some sort of distance. So that should clue in that we're going to be solving for work or using work to solve. So work is just going to be our change in energy. Work we know as F delta D. Our change in energy here is our change in velocity, essentially, which is going to go from 8.9 to 0. So we have 1 over 2 mv2 squared minus 1 over 2 mv1 squared. But we know that since v2 is going to go to 0, this whole thing is going to go to 0. And we're left with F delta D equal to negative 1 over 2 mv1 squared. Our force, negative 7,000 newtons, just pointing in the direction opposite. These are all vectors here. And then negative 1 over 2, 1,000 kilograms times 8.9 meters per second. We can rearrange and solve. This leaves us with a change in distance of 5.6 meters.